In organic chemistry, oxidation is often associated to increasing of the oxygen content of the molecule or decreasing of the hydrogen content. Reduction, on the contrary, is often associated to decreasing of the oxygen content and increasing the oxygen content. We could also utilizing the traditional oxidation state to look into oxidation and reduction. When oxidation state increase, we see this atom is oxidized, and when the oxidation state decrease, we see this atom is reduced. In order to assign the oxidation state, we need to know the electronegativity of these atoms. Okay, so when carbon and oxygen form a sigma bond, because carbon is more electronegative, we can assign the electrons between carbon and hydrogen to the orbital of carbon. And same thing for the rest of the 3 carbon-oxygen sigma bond. Therefore, to assign the oxidation state of carbon, you use the number of valence electron of carbon minus the number of electron that's assigned to carbon, which is 8 in this case, and the answer is the oxidation state of carbon in this molecule. So in the case of methane, carbon has an oxidation state of -4. When you have a carbon-oxygen bond, like what you see in methanol, because oxygen is more electronegative, the pair of electrons between carbon and oxygen will be assigned to oxygen, and therefore the oxidation state of carbon in methanol equals 4 minus 6, which equals -2. So in this case, the carbon has a -2 formal charge. Okay, and when carbon and oxygen forms double bond, all the 4 electrons are assigned to the more electronegative oxygen. Therefore, in the case of formaldehyde, the oxidation state of carbon equals 0. In the formic acid, you have a carbon that single bonded to a hydrogen and bound to 2 oxygens through sigma bond and a pi bond. And you know that there's only a pair of electrons that can be assigned to the carbon over here. So the oxidation state of carbon equals +2. You don't have to write positive, but it's always nice to write it. In the case of carbon dioxide, because carbon is double bonded with 2 oxygen over here, so there is no electron assigned to carbon. Therefore, the oxidation state of carbon equals 4 and this time it's +4. Don't think I did a good job. I'm gonna erase it, write it again. It's +4 over here. All right. So what if you have same atom bound together? If you have same atom bound together, just like in the case of ethane, ethylene, and acetylene, and you would assign the electrons between the same atom equally between them. That being said, for a carbon-carbon single bond, you would consider that these 2 carbons are equally sharing that pair of electrons. So you would assign each of the carbon with 1 electron. Therefore, for each of the carbon, the oxidation state equals -3. Okay, that's a 3, not a 5. Right? So in the case of the ethylene, the oxidation state of each individual carbon equals -2. And in the case of acetylene, each individual carbon has an oxidation state of -1. So hydrogenation of alkyne to alkene, of alkene to alkane are all essentially reduction reaction. Okay, and the example earlier from methane to methanol, formaldehyde, formic acid, and carbon dioxide, from left to right, the oxidation state increase, and therefore the converting a species from left to right is an oxidation reaction. And converting any of the species from right to left is referred to as reduction reaction.